Yeah.
Yeah. Yeah. Okay. All right. Yeah, I'll be ready whenever you want to.
Okay.
Whenever you want to start now.
Great. Thank you. So Aleks, yeah, where are you from?
Where am I from?
Okay.
Where am I based? So
No,
I'm in
where are you
Oxford.
from? Where are you from originally? If it's okay for me to ask.
Yeah, I'm from Oklahoma, Tulsa,
From
Oklahoma. Yeah.
Okay.
So I guess,
have you ever been to Mexico?
Only just to the border, like the classic thing American teenagers do of driving down and enjoying the lower drinking age. But yeah, I'd like to go for go there properly sometime.
Yeah, that'd be very nice. Yeah. Okay. Well, I'm sorry. I think maybe we should go ahead and start. So I'll just introduce you formally. Okay, so welcome everyone to this new session of our category seminar here at UNAM. So it's my pleasure to introduce today's speaker, Aleks from Oxford, who will be speaking to us about star autonomous categories and causality in higher order processes. So the title of his talk is A Categorical Logic of Consistency for Causal Processes. As always, if at any point wishes to ask a question or make a comment, please go ahead and unmute yourself and ask a question or make a comment. If you you can also ask the questions in the chat, and in that case, I can interrupt Aleks for you. So we will also be having a questions round at the end of the talk. So yeah, thank you very much, Aleks. Yes, please take it away.
Okay, thanks, Juan. Thanks for inviting me to this seminar. So I'm happy to be here. Let me share my screen. Yep. So this is are my slides visible now? Yep, thumbs up, good. Okay, and I think, yeah, that stuff's sort of out of the way. Okay, yeah, so as Juan said, the title of this talk is A Categorical Logic of Consistency for Causal Processes. If you saw a talk I gave in the QISS seminar, I guess it was probably 4 or 5, 6 months ago. Now it's hard to keep track of time in COVID days. Then some of this will probably look fairly familiar, but I've categorized it a little bit more for this audience. Yeah, let me just start with some context. So or what I see as the kind of goal here. The goal of the things I'm going to talk about is to do what I call black box causal reasoning. So what I mean by this is you have some named agents, events, probes, points in space-time, whatever you want to think of them as. And the question is, can we model, observe, and prove properties about their causal relationships in a way that's relatively independent to the actual concrete details of whatever theory we're talking about? Okay, so the kind of setting you might want to look at is, for example, this shared device type setting. So this could be like a Bell type scenario if you're familiar with these kinds of things, where you have a bunch of agents and they're sharing some sort of device or devices which are networked to each other. And I represent this just as a big box, and each agent has an input to that box. So here's A's input, and they have an output as well. So there's A's output. So if you're thinking in quantum terms, the input could be a choice of measurement, and an output could be a measurement outcome. Okay, so that's a very common situation if you want to look at, for instance, Bell scenarios, quantum non-locality, to look at these kinds of situations and try to characterize these boxes. So for instance, who can talk to who has local correlations with who, and who has potentially non-local quantum or maybe even post-quantum type correlations. I think this is an interesting scenario, but also the dual of this scenario it's quite interesting, and maybe even more interesting, where rather than thinking about having a shared device, you have a shared environment. So now we think that each agent actually gets an input from their environment, and then decides to do something with it and then produce an output. So you can think of this as local labs where each person has a kind of an inbox and an outbox, and they get something in their inbox. It could be a bit of classical data, or it could be some quantum system. They do some process to it and then they produce an output. And now the interesting thing is that these agents can be put in different kinds of causal orderings because we've kind of black boxed the universe that they live in. So I can imagine wiring this up in all sorts of interesting ways. Right, so for instance, if I had a pair of agents, I could think that what's really inside of this box is wiring the agent on the left before the agent on the right. And then if I plug their processes into this thing, which is now a higher order process, then it does just that. It plugs the first process in before the process, the second process, right? So I'm always drawing inputs going in the bottom of these pictures and outputs going out the top. Right, but you can imagine, since this is black boxed, well, it could have been the other way. So if secretly this wiring was this way around inside the box, then when I plug in these processes, then it will compose the second process before the first one. But then also this situation allows for more general things. So I could have, for instance, some lack of information about the causal ordering between these two agents, which I can represent as a kind of probabilistic mixture. So maybe with some probability P, Alice is before Bob, and that's what this part of the mixture represents. And then with some probability 1 minus P, Bob is before Alice, and that's what this part of the picture represents. Okay, so you could have this kind of mixed causal ordering inside the box, or you could even have superpositions of causal ordering, or in this case, a kind of, what's happened here is now I have a kind of a control system and it's being entangled with the causal ordering here. So this is the quantum switch. If you're familiar with these kinds of things, this is a very typical process which has indefinite causal ordering. Okay, and all of these things I'd like to be able to study within this framework of black box causal reasoning. Okay, so yeah, I mean, this audience has encountered this line of work before. I see some familiar names from the sort of QISS crowd. So these kinds of processes have been have attracted a lot of interest, especially in foundations of physics and even in experimental physics lately, studying processes which hypothetical processes which can't be put in a causal order, and even trying to do some experimental realizations of things like the quantum switch using photons. Okay, so that's the goal, or the vision, let's say, of what we want to do. The setting for this is process theories. So what is a process theory? Well, a process theory is a symmetric monoidal category plus some extra thing, a special family of processes, which are the discarding processes. So these are things which operationally you should interpret as throwing a system away or choosing to ignore a system. Maybe more mathematically, you could think of it as something like tracing out a quantum system or marginalizing. Okay, so I guess because this is a categories group, everybody is more or less familiar with what symmetric monoidal categories are. Is that a safe assumption to make? Getting a thumbs up from one. So that's good. I can sort of go through that bit quickly. I mean, I don't go to much detail here anyway. The thing that is maybe a bit different from your standard literature on monoidal categories is that we do everything in this pictorial notation. So we use string diagrams to represent everything, where we really have boxes, and putting them side by side is the monoidal product, and plugging them together is the categorical composition. And we use this process theoretic terminology where a morphism or a process coming from the tensor unit or the trivial system, we call that a state. So that's like having something where you don't care about its past and you're preparing it to be a specific in a specific state. We call that process a state. You can think of it as a preparation process. And then the dual of that is an effect. So something whose target is the tensor unit, we call that an effect. Okay, and yeah, as I said, we use the string diagram notation. So categorical composition looks like this. Monodal product looks like this. Identities just look like a bit of wire. The identity on the trivial systems, the identity on the tensor unit just looks like blank space. And I can think of that as the scalar 1. Usually this represents the probability 1 in my process theory. And swaps are just wire crossings, as you would expect. And as I said, the thing which makes process theory special is that you have this distinguished discarding process. Okay, and in this very lightweight framework, we don't really assume anything about discarding. We'll use it to make some definitions. The only thing we really assume about it is that it gets along well with the monodal structure. Okay, so if I discard the tensor of two things, that's the tensor of discarding those things. And if I discard nothing, that's the same as doing nothing. Okay, so process theory is a symmetric monodal category with these discarding processes doing this, and that's it. So the point of having this discarding process around is that it enables us to make some more definitions inside of this category, and we can start to give some operational interpretations to these processes and different kinds of processes we might want to study. So the most basic kind of definition is what we actually just call causal, which is confusing sometimes because lots of stuff actually gets called causal in this whole area. Some people call this normalized or terminal or something like this. But the intuition is, so a process is causal if it satisfies just this equation. So I discard its output, that's the same as just discarding the input. The interpretation of that is that if the outputs of a process are ignored, it doesn't matter which process happened. Okay, so if you think about this a bit like a computer scientist, you might think that this running this process has no side effects. Okay, so if I don't care about the output of the process, then I might as well just not do it. Okay. In something like quantum theory, this is like saying that the process is a deterministic one. Okay, so that process can be done with probability 1, which is the usual interpretation of being trace preserving. Right, so a consequence of this is that a causal process only affects other processes which consume its outputs. And as a consequence of that, I can think of a diagram of processes which are wired together, well, in particular, causal processes which are wired together as being a kind of causal diagram, in the sense that a given process in this diagram will only affect things in its future. So I can look at the boxes which are kind of wired to the future of that thing, and that's the only place that a process will have an effect. I see that something appeared on the chat. Is that a question?
Yeah, that's a question.
Yes. Does discarding correspond to some kind of terminal object? Yeah, so if you have a process theory where all of the processes are causal, that's the same thing as saying your tensor unit is the terminal object. Okay, so which is the same thing as saying that there's a unique effect. Okay, so there's a unique causal effect, which is the discarding. And if you were a category theorist, you would write this thing as the exclamation mark. So it's like the terminal arrow. Here we don't assume that everything is causal from the get-go, because it will actually be quite interesting to look at processes that are causal and not causal and sort of compare them to each other. Let's see. Thanks. Okay, you're welcome. So yeah, so a consequence of causality is a process only affects other processes which consume its outputs. Okay, so you can really think of this wiring as a sort of causal ordering of these boxes, especially if I don't put any sort of feedback loops with my wires. Okay, I think I need to, yeah. Okay, so some special cases of causality. Well, there's only one causal effect. Okay, so you should think of this causality equation on this slide as really this means if I discard all of the outputs, that's the same as discarding all of the inputs. So in particular, if I don't have any outputs and this thing is going to be causal, then it has to equal discarding. Okay, so here on this side I've discarded nothing, which was all the outputs, and that means that I should discard the input. So any effect has to be this discarding effect. Okay, and causality for states means normalization. And we'll see that this really means normalization on the nose for the kind of concrete process theories that we're interested in. But remember that I said that I write this bit of empty space or the identity on the tensor unit, I write that as 1. So you can think of that as the scalar 1. So discarding a state equal being causal, that's like saying that you know, tracing the state or summing over the elements of the state gives me 1. It's like a normalization property. Okay, so something that's slightly more intricate than just plain old causality is you can also impose signaling conditions on boxes which have multiple inputs and outputs. Okay, so maybe the simplest non-trivial signaling condition is to say that a box is one-way signaling. Okay, so this equation says that Alice, so Alice is this input-output pair A and A prime, and Bob is this input-output pair B and B prime. This equation says that Alice can send a message to Bob, but not vice versa, using this box phi. Okay, so in particular, if I get rid of Bob's output, so this is like focusing on Alice's perspective. If I get rid of Bob's output, then you can see that there's no wire from Bob to Alice. Okay, so that's why this equation captures the fact that this is only one-way signaling. And in particular, it captures the fact that there's a potential for Alice to send a message to Bob, or put another way, it's impossible for Bob to send a message to Alice. Maybe that's probably the right way to think about it. So it could be that it's just not signaling at all, but here the only possibility is that Alice could send a message to Bob once this is imposed. Okay, yeah, so Alice can send a message to Bob using such a process, but not vice versa. So non-signaling is just that equation and then the symmetric one. So where if I discard Alice's output, that becomes discarding Alice's input. Okay, and this is the usual notion if you think about non-signaling boxes in foundations of physics. This is the usual notion of non-signaling that you encounter there. So this is more general than being separated. It's more general than being a tensor product of two boxes, because Alice and Bob's outputs are still allowed to be correlated here. So they can have some shared randomness that correlates their outputs, but they can't use these correlations to send a message between each other. Okay, so Alice and Bob cannot communicate with a non-signaling box. Okay, so in the classical case, the simplest classical process theory to take is matrices of positive numbers. So in this process theory or this category, the objects are natural numbers, which I think of as dimensions, and the morphisms are just matrices of the correct size to be something which goes between those dimensions. In that case, discarding is the row vector. So it goes from say like k to 1. So that means it's a 1 by k matrix. It's a row vector with all ones there. Okay, and the reason that we set up discarding this way is that if I now discard a state, which is a column vector, then this exactly corresponds to the fact that if I sum up all the entries of that column vector, I get 1. Okay, so now row here, a causal row, is a column vector of positive numbers summing to 1. So it's a probability distribution. Okay, so here we're really working with just classical probability theory, even on finite systems. So really the simplest kind of classical probabilistic theory you could come up with. Okay, so the causal states are probability distributions. The causal processes are stochastic matrices or stochastic maps. So these are just matrices where all of their columns individually sum up to 1. And then the signaling conditions are conditional independences of conditional probability distribution. So if you've seen conditional independences before, these things will probably look familiar to you. Here, if I've marginalized out B prime, this says that this conditional probability doesn't depend on B anymore. If I marginalize out A prime, then this conditional probability doesn't depend on A anymore. Okay, so if I run through those equations on the last slide, in this concrete process theory, it corresponds exactly to these conditions on stochastic maps. Okay, so the thing you would expect if you've seen signaling conditions before. Okay, in the quantum case, the process theory, the simplest quantum process theory to work with is CPM. So this is a process theory whose objects or whose systems are Hilbert spaces and whose morphisms are completely positive maps. And then discarding is the trace. So trace is a completely positive map from a arbitrary Hilbert space to the trivial Hilbert space. Okay, I can see it in that way. So discarding is trace, and then of course discarding a state equaling 1 is just saying that the trace of that state is 1. Okay, so the states are density operators and the causal processes are trace preserving quantum maps or quantum channels. And then the signaling conditions are, I just wrote this as the standard signaling conditions in terms of the partial trace. So it's a bit messy to try to write that very symbolically. In fact, it's easiest just to draw the pictures of what those are. Okay, so now I guess are there any questions about that? That's just the kind of foundational framework. I don't think there was anything in the chat. It looks like everyone's pretty happy about that. Okay, so now what about this higher order structure that I was talking about before? How do we get the higher order stuff in? Well, because I grew up in Oxford. Well, I didn't grow up in Oxford, but I grew up academically in Oxford. As soon as I see higher order structure, the thing I want to do immediately is this stuff, to start bending wires. Okay, so in fact, a very simple way to get something kind of higher order in is to look at compact closed categories. So a compact closed category, well, it has a categorical definition. Every object has a dual, and that means that you have a pair of these maps, and the wires yank, and so on. But the way that you could say that, to somebody who doesn't know about these things, what a compact closed category is, it's a process theory, but it also has what's called map state duality. So a generic map from A to B can be thought of as a state on the joint system of A star B. So A star is like the dual space of A. Okay, so this set of processes is isomorphic or in bijection to this set of joint states in a compact closed category. And in quantum theory, if I do this in CPM, this is exactly the Choi-Yamaokovsky isomorphism. Okay, so it's the kind of familiar notion to a quantum theorist of how to do this, of passing between states and processes. Okay, and here's the actual definition. For every A, there exists an A star, which I think of as the dual, something like the dual space of A, and a pair of maps, one out of the tensor unit, one into the tensor unit, satisfying these yanking equations. Okay, so I just yanked the wire. So these are very easy to remember. So yeah, and this implies this bijection. Okay, and it implies it in a very nice way that's very easy to work with. So the point of doing that, of turning processes into states, is this gives us a very simple way of talking about second order processes. Okay, because now if I can think of this now system consisting of processes from A to B as this joint system A star tensor B. Okay, so I can think of something which takes processes from A to B to processes from C to D as a box which takes this joint system that joint system. Okay, and that's exactly the data I need for such a second order process. So if I really want to start working with these things in a kind of higher order way, I just make a slightly better notation. And rather than writing this as a box like that, I'll write it as this Pac-Man shape, which is really making it clear that I want to put a process in here as my input, and I'll get overall a process from C to D. Okay, but this is all just kind of syntactic sugar. Let's say you could translate without ambiguity, get rid of all the Pac-Man stuff, and just work with these kinds of first order boxes, because it's always clear what gets wired where. Okay, so this is a very simple way of getting some higher order structure. The problem with this is it's somehow too simple, okay? Because in a compact closed category, the dual, the star, it actually distributes over the tensor product. And a consequence of that is that there's no genuine higher order processes, or at least every higher order process is equivalent to a first order process. Okay, so to show you what I mean, I can give you an example. So here's a higher order process. It takes a map from A to B as its input, and it gives me a C as its output. Well, if I unfold the definitions there, that's something that looks like this. Okay, so first I unwrapped kind of outside the brackets, and then I unwrapped inside the brackets. But then since I can push this star over a tensor, then I get something like this. And then if I shift things around, then I can see that actually this process is, or this space of processes is equivalent to this space of processes. Okay, and this was a higher order, a second order thing, and this is a first order thing, right? It's just processes from B to A, tensor C. The only thing a compact category can really remember is whether something wanted to be an input or an output. So it kind of remembers the polarity of your types, but it doesn't remember anything else. It doesn't remember anything about it being kind of higher order. Which, when you think about these higher order causal things, is a problem, because being second order causal, so preserving causal maps, is a different condition from just being a causal map. Okay, so somehow, in order to get those things in a category, we'll have to have a category which can tell the difference between those things.
I'm sorry, Alex, we have a question by Jack.
Yeah, let me just open it up. Reynolds defunctionalization. I don't know what that is, Jack. do you wanna clarify?
Yeah, it's a whole program transformation from programming languages. When you have higher order functions in a whole program, you then know you always have finitely many of them. So you can always give them a name, create an apply function, and remove them all. So in a whole program context, you can always remove higher order functions. Not in a library context.
Right. Okay. Yeah, I think that there is some aspect of that here, because once everything is already composed, typically it does make sense to just think of that as a channel or as a state, so not as a higher order thing. But it also makes sense to think of higher order things, so processes which want processes as inputs. And those don't collapse. So I think you do start to see the same kind of thing like you're talking about.
Yeah. So here the overuse of the word is bad. In a closed setting, a whole program, they disappear. But in an open setting, then it's different.
Yeah. Yeah, that's interesting. Okay. Yeah. So yeah, I would say in this case, because this is an open setting, this is bad that everything collapses. But you can fix this in a fairly easy way. Obviously, the problem is just this equation. So let's just get rid of it, right? So let's let's not impose the fact that the star distributes over the tensor. And when we don't impose that, we actually now get two tensor products rather than one. We get this tensor product, and we also get its De Morgan dual, which we write as this upside down ampersand, which gets called the par. So now we have two different ways of making a joint system, okay? And I think kind of intuitively, you want to think of the, especially in this case, you want to think of the tensor as like the little one and the par as the big one. Or you can think of the tensor as like the one that's kind of like and the par is something that's kind of like or. So if I think of star like not, then that's what I mean by De Morgan dual here, right? That's not A and B. If I take the not of all that, that's like A or B. Okay, so what's the recipe for getting a star autonomous category? Well, I take a compact closed category, which I think of as my raw materials category. So this is the ones which have my maps, but nothing about being causal or normalized or anything like that. This category needs to have a kind of a well-behaved discarding, so it satisfies some properties which are convenient. And then I make a construction called the cause construction on C, and I get a star autonomous category, which inside of it has this kind of logic of causality, logic of causation, which I kind of advertised in the title of this talk. Okay, so if I do this for matrices of positive numbers, I get higher order stochastic maps, which if you've sort of hung around in sort of probabilistic programming semantics, you might have heard this term probabilistic coherence spaces. Those are basically the same thing as higher order stochastic maps. And if I do this to CPM, I get higher order quantum channels. And basically all of these indefinite causal structure things you've seen, like process matrices or the switch or quantum combs, all of these things are instances of these higher order quantum channels of various different types. And I think an interesting game to play here is to take some other raw materials category and do this and get non-standard causal models. I haven't really thought of any good ones yet, but I think that still would be something fun to do. Taking the category of relations does actually give you some interesting stuff here. So that's one that's kind of fun to do. Okay, so what is this construction? Well, if you know things about linear logic or models of linear logic, it's a double gluing construction. So if that means something to you, great, then you can just switch off for the next couple of slides. But let's more concretely, I take my category C and I make a new category where the types are pairs. So a pair is an object or a system for my base category, and a subset of the states on that system. Remember, states are morphisms from the tensor unit to A. Okay, so I take a subset of the states where this set is closed, and I'll say what closed means shortly. Okay, so I want to think of this as I have a system and I have a set of states which I declare to be my good states, like my causal states. Right, so for a first order system, these are just my normalized states, like my density operators. But for a higher order system, these could be like my trace preserving maps or other more general things. And then the processes are just things which preserve those sets. Okay, so if I have something in this kind of blessed set of states for A, then if I do a process, then it's a good process in this category if it preserves that set. So it takes it into the blessed states for B, okay, the causal states, let's say. Okay, and I haven't told you yet what this star is, but I'll tell you soon. But taking the star of both of these things makes it into a star autonomous category. Okay, so I'll tell you what the star means for a set of states now. Well, it takes a set of states to the set of effects which are normalized for that set of states. Okay, so it's the set of pi such that for all rho in C, just plugging these things together gives me 1. Okay, so for example, if I take the set of all normalized states and I take its dual, the only thing in that dual is the discarding or the trace, okay? That's the only effect which is sort of good for all of those. But for higher order stuff, you get more interesting duals. Otherwise, this wouldn't be a very interesting category. Okay, so the star is always a way of passing between states and effects which are normalized for those states. Okay, so in particular, if I do this twice, I get back to states again. Okay, so if I take the dual of a dual, then you know I'll have effects on a star, which is the same thing as states of A. This is just the same thing as saying that an object is the same as its double dual. Okay, so C star star is a set of states again, and being closed just means that this thing is equal to its double dual. Okay, so I'm just defining closed to mean that C is equal to its double dual. So I can prove that star star is a closure type operation, so it's idempotent. If I take the star star twice, this is always just doing it once. And being closed is just being equal to this. Okay, so yeah, maybe I'll just let that sink in for a minute if you're not used to all this sort of states and effects stuff. Concretely, what you should think of this closure like is like being an affine subspace. Okay, so in the quantum case, these closed sets are all positive affine subspaces. So you take an affine subspace of your set of states, and then you just restrict to the positive ones there. Okay, so that's, you know, it's not just a generic set, but it can be a kind of a weird shaped space. You see, so maybe I should I admit this this person? Yeah, there we go. Yeah. Okay, so that's what closed means, and that's what gives this category its nice star autonomous structure, is the fact that these sets satisfy this nice property. Okay, so what are my tensor and my par here? Well, the tensor is the smallest closed set which contains all the product states. Okay, so I can form the tensor by taking all of the product states of these causal states of my two systems, and then I close it. Okay, and in fact, if you work out, you know, what are all the joint probabilistic states or all of the entangled states, you can actually do this. You can just take all the product states and you take the affine closure, look at the ones in there which are positive, so which give you good quantum states, and this is all of the quantum states. Okay, this is all the normalized quantum states. Okay, so this is the smallest set which contains all the product states, whereas par is the biggest set which is normalized for all the product effects. Okay, so now I take an effect on CA and an effect on CB, and then and then rho is in this set if it's normalized for that product effect. Okay, so if you've ever spent some time thinking about generalized probabilistic theories, and you know about the minimal and the maximal tensor product, this is kind of the same thing going on here. You can think of the tensor as like a minimal tensor product, and the par is like a maximal tensor product. But there's kind of a difference here in that everything is positive everywhere. So we're just doing it with normalization. We're not doing it with normalization and positivity at the same time. Okay, so if you know about GPT stuff, that bit of waffle might make sense to you. Otherwise, just let it roll over you. Okay, so that's what these two things are. And in fact, as is typical in a star autonomous category, we want to use the par to define our set of maps. Okay, so the space of maps is going to be A star par B. Okay, because the space of maps should somehow be the bigger thing. Whereas if I took a tensor there, these would be like the kind of separating or the constant maps, which is something that you can prove. Which is not all of the maps, of course. Okay, so as an example, it's always good to look at what first order systems look like when trying to understand this category and its structure. So first order systems are systems of the form of I take an object A and then I just take the dual of discard. So that means I take all of the states which are normalized for discarding. Okay, so for a quantum system or a classical system, this is really just taking all of the normalized states on that system. Okay, so if I form the tensor product here, well, I take all of my product states and I take the double dual. Well, the only thing in the dual of my product states is going to be discarding. And then if I take the dual of that, that's all of the states on that system. Okay, so the tensor product of two first order systems is just the set of all normalized states. Again, as you might expect. Now, if I look at the par, well, I should take all of the effects for each of the systems and then look at all the states which are normalized for all of the effects. But then there's only one effect for a first order system, which is discarding. So this is all of the normalized states. Okay, so tensor is all of the normalized states, par is all of the normalized short states. Okay, so tensor and par are the same for first order systems, right? Which is why I think if you went to if you took a first course in quantum mechanics, they wouldn't teach you what the par of two quantum systems is, because at the first order it doesn't matter. We can take either tensor product, they're the same thing. But of course, this is only interesting because there are occasions where tensor and par are not the same. And the first instance where this gets interesting is if I look at taking tensors of systems of first order systems, so of systems of maps. So if I take all the maps from A to A prime and all the maps B to B prime and I form their tensor product, this gives me all the non-signaling processes. Okay, so the things in there are exactly the joint or the bipartite processes satisfying the non-signaling conditions. Okay, so that's the tensor product. If I take the par, and remember how I said I should think of tensor as like the small space and par as like the big space. If I take the par, this is just all the processes. Okay, so the processes here are allowed to signal arbitrarily, whereas the processes here are non-signaling. And there's a natural embedding of the non-signaling processes into the space of all processes, because they are processes after all. So you can ask, what lies in between here? Well, I can define one-way signaling processes as things of this kind of shape. So here it's like, if you give me an A and you give me a process from A prime to B, then I'll give you a B prime. And in fact, if I write it in this kind of way, it becomes more clear. If you give me an A and you give me a process from A prime to B, then I can give you a B prime. This is like something where Alice can talk to Bob, but not vice versa. And one-way signaling is like if I discard Bob's output, then all that's left is Alice's process here. And that's a comb. That's a quantum 2 comb, if you've seen these things before. So I get this kind of ordering of, I've got non-signaling kind of as the smallest thing here, and I have these two one-way signaling processes. Here's Alice before Bob and Bob before Alice. And then at the top, I have all processes. Okay. And now the interesting thing is if I take this ordering, sorry, that went a bit fast. So if I take this ordering and I just dualize everything, so now I'm just going to put a star around all of these types, then all the arrows will flip around, because if I have sort of A going into B, well, then B star goes into A star. So all the arrows flip around, and you'll see that if I take the dual, I get interesting stuff here. So here's a process, a kind of second order process, which takes an Alice lab and a Bob lab. And the smallest thing is now the par, but it's been dualed. And you can show that these are just the correlations. So there's no communication between Alice and Bob here. And then the two things in between are two combs. So this is where either Alice's lab is happening before Bob's lab or vice versa. And then the biggest thing is process matrices. So this is where there's no signaling or no causal ordering whatsoever imposed, and you can even have indefinite causal ordering inhabiting this type. Okay, and these are quite interesting things because this is where all this indefinite causal structure lives. And in fact, so if you look at the types of these things with indefinite causal structure, then the quantum comb is something of this kind of type. You know, it's got a control system, and then it takes a couple of processes, and then it's got an output of your control system. This OCB process matrix, which is the thing which violates some causal inequalities, is something of this type. And the interesting thing to note is all these indefinite causal structures have negative occurrences of this type, of this tensor of two processes. Okay, so there are things which always take a tensor of two process types as input. And the reason that it's interesting that it takes the tensor as input is that it's now allowed to kind of wire it up in sort of arbitrary ways because it's a non-signaling process. I can do that without creating sort of feedback loops and so on. Okay, so the point of having all of these things wrapped up in a category is that we can start thinking about composing them. And I think, especially with higher order processes, there's been a lot of confusion around composition of them. And I think thinking about it more categorically, you can try to kind of get your head straight about what's really happening when we start to put these things together. So, I mean, at the first order, things are simple, right? We have sequential and we have parallel composition, and these sort of suffice to build all the composition that we're interested in. For higher order processes, this is not so simple, right? So for one thing, if I have a thing by insert, you know, whatever value of thing you like, so maybe a process matrix. So thing tensor thing is not typically a thing again. So, and something I'll show is that if you take two process matrices and you take their tensor product, this doesn't give you just a process matrix on bigger labs. That's not what you get. You get something that's more subtle than that. And there's also many ways to plug higher order processes together, and only some of these are well defined. So the things which are not defined is where you introduce a time loop, because this totally destroys normalization and you can create kind of logical paradoxes and this kind of stuff. Okay, so here's the example that I just mentioned. If I take two process matrices and I try to put them in parallel, so I take their tensor product, you might think that okay, if Alice and Bob now share two process matrices and you know, one of them is a qubit process matrix and the other one is a qubit process matrix. Well, maybe they now just have a 2-qubit process matrix, which is what this picture is supposed to show. But in fact, this isn't the case. And what you can furthermore show is that there's no reasonable bilinear map which sends a pair of arbitrary process matrices to a process matrix. Okay, so reasonable means, you know, it needs to satisfy things like a tensor product would typically satisfy. I guess you can probably always just throw away one of the process matrices or something like that, but that's not what I mean by reasonable. And the reason for this is fairly simple. If you think about a pair of process matrices, well, these are allowed to signal in either direction. Okay, so if I have two of them, you can imagine that one of them is signaling from Alice to Bob. So that's this W on top. And then one of them is signaling from Bob to Alice. That's this W on the bottom. And now suppose what Alice and Bob both do is they take their left input wire and they plug it into their right output wire. And maybe Alice does a NOT gate when she does that, okay, if they have a bit or something. And then what you get in this overall thing is a time loop. So you can trace this wire all the way around, right? I get a time loop here. And what happened is I have a bit which sort of travels to its own past and you know, kills its grandfather or something, I get a not gate. So here I get a paradox. And you can see that, this whole thing will evaluate to probability 0, which means basically that it's a paradox. If I don't put a not gate there, it'll evaluate to probability 2, which again means that there's a paradox. And these are two different kinds of logical paradoxes. One's called the grandfather paradox. The other one's called the information paradox, perhaps, or bootstrap paradox. Something like I have a system, but it never began, right? It just goes round and around and around. Okay, so how can we tell if a composition is allowed? Well, so in a compact closed category, it's like the 60s. Anything's groovy. You can just plug anything into anything else. In particular, you can create a time loop like this. But star autonomous categories have an internal logic which tells you if a composition is allowed. Okay, so as I kind of mentioned before, I can think of all of these connectives of my types as logical words, like tensor is and, par is or, lollipop is implies, star is not. And all of these things read in the right kind of way. If you think about the kinds of equations I've shown you so far, right? So not A or B is the same as A implies B, right? So this all works out very nicely. Here's the De Morgan dual thing: not A or B is not A and not B. So what's the rule? This is kind of how an internal logic works for categories. This is how categorical logic works. The rule is a composition is allowed if it corresponds to a tautology in the internal logic of the category. So if it's some statement that I can prove in the internal logic. Okay, so you can ask, is this allowed? Well, I write down this logical statement and I ask, is this a tautology? Well, this is A implies B or B implies A. Well, this is not a tautology. Well, at least, not in the kind of logic we have here. It's not the case that A has to imply B or B implies A. That's just something that might be true, but it's not a tautology. But now suppose I plug a process into the dual of a process. Okay, so here's the type of two things that I might want to plug together here. And now this says A implies B or not A implies B. Well, this is like excluded middle, right? So A implies B. So this is like a P or not P thing. And I haven't told you what this logic is yet, but this is a logic that has excluded middle. So this is a tautology. So this composition is allowed. So what kind of logic is this? So here's some things that are fine, that are allowed. But these things are kind of familiar from classical logic. Here's something which doesn't hold in this logic. So it's not the case that A implies A and A. So it's a resource sensitive logic. It's a linear logic if you're familiar with these things. So if I have an A, I have one A. I can't get lots of A's out. So it's like a what is it called? Like the logic of food, logic of stuff. If I have an A, I have exactly one A. And this is like having a no cloning type theorem in your category. Okay, and what this logic is, it's called MLL plus mix. So MLL is multiplicative linear logic, and mixing is the mix rule. This is basically saying that tensor embeds into par. Okay, so here's, I guess these guys are all the linear logic rules, and then these two are the mix rules, which imply tensor embeds into par. Okay, so this is just written in a kind of a more formal, sequent style notation. Okay. Thanks. See you later. Thanks for listening so far, Robert. There's not too much more I have to say here. So yeah, MLL has been around since the 80s. It was invented by Girard. And And then the nice thing about a logic that's been around for a long time is some nice tools for working with this logic have been around for a long time as well. So automated theorem provers for MLL have been around since the 90s. So in fact, the kind of final thing I want to show is traveling back in time to 1997, when things like Titanic and Face Off happened, and when computers looked like that, and when we were all surprised when a celebrity was gay. So let's go back to 1997. So here we are. As you can see, this is a slightly later version of Vim than was available in 1997, but you know, you'll have to use your imagination. Okay, so here's some notation. The tensor is just the asterisk, right? The par is the plus. Map is arrow rather than lolly, and dual is this tilde. Okay, so let's consider we have a kind of a non-trivial situation here to give to our theorem prover and get some interesting answers about causality. So let's take 4 parties. We have Alice, Bob, Charlie, and Denise. And each of these has an input, which is called their name 0, and has an output, which is called their name 1. So Alice's input and output are A0 and A1. Okay, and imagine that Alice and Bob are in some possibly indefinite causal ordering. Okay, so they're in a, maybe I should zoom out just a little bit here. Is that still, I guess that's still visible? Okay, so Alice and Bob are in some possibly indefinite causal ordering. I hope you like my ASCII art here. And the way I express that is I take this type of non-signaling processes and I take its dual. And now as a kind of a sanity check, you know, we can look at some special cases. So a special case of that is that Alice comes before Bob, that they have a 2-comb where Alice is in the past and Bob is in the future. And you can ask, you know, does being a 2-comb imply being a process matrix? Okay, so that's what this statement says. So the thing above the long arrow says I have a 2-comb. Right? And then does that entail being a process matrix? Well, I can send that to the theorem prover, and it says yes, right? So here's actually a proof tree, so a formal proof that is indeed the case. Okay, you might not be able to see quite all of it there, but it can say yes, and it can even give you the proof of why this thing is a tautology. That's a linear logic proof there. Okay. Now here's Bob before Alice, right? So that should also be a special case of being a process matrix. So we can ask, is Bob before Alice generalizing the statement where I don't have any causal constraints? Oops, sorry about that. Yes, and here's the proof. I guess when I say yes, I think what I'm reading is this this part which says yes right there. It gives you a proof tree and it says yes. Otherwise it will, I don't know, it would probably say no, or it will say I don't know. In this case, I think it'll always say yes or no. Okay, and of course, a very special case is neither Alice and Bob can talk to each other. So this is only shared correlations. And the type of that is I take the par of their 2 processes and I take the dual of that, right? So this was the thing that was right at the bottom of that dual picture, right? And that should be only correlations. And I can ask, does only correlations generalize no causal constraints? Yes, it says, right? Okay, so those were just kind of sanity checks. We've not done anything we didn't already know the answer to here. But now let's try something that's a little non-trivial. So we had Alice and Bob over here, and they're sharing a process matrix. Now let's take Charlie and Denise, and they're also sharing a process matrix. Okay, so they have they're in some possibly indefinite structure. And furthermore, Charlie and Bob share a non-signaling channel. Okay, so if you didn't follow all of that, you're about to get some pretty epic ASCII art showing exactly what's going on here. So here's a pair of process matrices. So I've got Alice all the way over here on the left, and then Bob sharing a non-signaling channel with Charlie, and then Denise all the way over here on the right. I just realized you can't see what I'm pointing at, but you know what I'm pointing at. So here's the whole picture. And now the question is, what do Alice and Denise have now? Okay, so what's the kind of the most general thing that Alice and Denise have? Anybody venture a guess? Maybe who hasn't seen some version of this demo before?
Yeah, it seems no one wants to.
No one wants to go out there. So the answer is that Alice and Denise only have correlations. Okay, there's no wire from Alice and Denise, and the reason is that there's a kind of a barrier here given by this non-signaling channel. So there's no way that I can sort of wire this up and then make a wire through here go all the way there. Okay, so if this was a generic channel, I could indeed do that. I could sort of wire through this channel from Bob to Denise, but since it's non-signaling, the only thing Alice and Denise can have is shared correlations. So we want to show. Okay, so here's that whole nice piece of ASCII art written as a logical statement. And the question is, does that imply just shared correlations? And that's this statement. And if I ask the prover, I think it will have to think a little longer, hopefully not too much longer. And it says yes. Okay, and then there's a slightly larger proof of the whole thing, which if I had prepared my Vim a little better, I'd be able to scroll back and show it to you. But just take my word for it that there's kind of a big proof up there somewhere. And yeah, it took what about 9 seconds to figure that out. So I think that's it for the demo. So that's an instance of taking a very old piece of software and using it for something that it was probably never intended for, which I think is pretty cool. So something that's still an open question is necessity. So I told you that if I can prove a logical statement in the internal logic, that means I can consistently compose these processes. I didn't tell you that that's the only situation in which I could consistently compose these processes. Okay, so provability in MLL is not necessary for these things to be consistent, but it is sufficient. So you can ask, well, how much richer does my logic need to be to get necessary conditions? Okay, and that's open. This could be well, maybe I'll just skip some of this stuff because we're a bit, yeah. So one thing that I think is quite an interesting way to get toward necessary and sufficient conditions is to extend this logic in a particular way. And that's to introduce a third connective, which is sometimes called seek for sequential composition. So this seek thing is a non-commutative connective. So A seek B is not isomorphic to B seek A, because I think of this as A before B now. And it's also its own De Morgan dual. Okay, so if I take the dual of A seek B, then that's A dual seek B dual. Okay, so somehow if you think about dual as kind of reflecting this stack of connectives, you know, around its center point, you know, then the par gets reflected over to tensor, the tensor gets reflected over to par, and seek sort of stays put right here in the middle with everything kind of pivoting around it. And you know, this was actually introduced mainly as a theoretical toy by Guglielmi as something to study deep inference. So this logic is an interesting logic from a theoretical point of view because it doesn't have a nice sequent calculus. You have to use this thing called deep inference, which is sort of a different way of doing formal proofs. So this was created as an example of where you really needed this way of doing proofs in this logic, which I mean, for me, deep inference kind of is categorical logic. And I think there's even some papers describing how these things are really related to each other. But classically, so in the case where I take those matrices of positive numbers, so I get, you know, higher order stochastic maps as my causal category, this exactly captures one-way signaling. So this A before B connective really captures A before B. So it does the causal thing that you want it to, which I think is a surprising coincidence that seek is exactly the thing that it seems like it would be. And there's also some nice completeness results there in the classical case. So for probabilistic coherence spaces, I think you do have something like necessary and sufficient conditions for this richer logic. But then an open question, well, actually the definition now I think is, yeah, let's say it's a little bit open, is how do we define a quantum seek? Okay, so we have a few different candidates for how to define this seek, okay, which are either totally abstract, so you can define it in the same way that we define the tensor and par, all in terms of states and effects and so on, or also very concrete, like you know, this thing is a affine combination of these kinds of blah blah blahs. So we have about 3 different definitions, and they all imply each other in weird directions. We don't know if they're equivalent to each other, and we don't know if any or / all of them satisfy this self-dual property. Okay, but if they do, then that's really cool because we're getting toward having this complete logic with this kind of funky non-commutative connective, which really captures, kind of gets to the heart of what signaling is. Okay, so that's, I guess that's all the technical stuff that I wanted to say. Maybe I'll just make a few kind of final remarks to step back a bit. The goal, or at least I think the big vision here, is to have a kind of a complete unified logic for doing causation with all different kinds of processes, classical or quantum or computational, what have you. And to shed light on some big questions about causal influence, causal inconsistency. So what are the most general notions which apply to all different kinds of theories of causal consistency? Can we sort of get practical, even computational advantages by thinking about these things more logically? So you can compute these consistency things very concretely, but the computations go very horribly exponential in the number of parties that you have. You're solving exponentially many linear equations or something like that. And if we have a good grip on how to compose these higher order processes, we can think about things like having, you know, emergent definite causal structures. So you could imagine having a sort of micro indefinite causal structure. And I can think about if I have a nice way of tiling a lot of these things together or composing a lot of these things together, can I start to see definite causal structure emerge, right? So can I start to get kind of toy models of you know, loop quantum gravity type stuff, where if you look at the really micro thing, then you have indefinite causal structure. But as you start to coarse grain a bit, then you see something that looks more like reality emerging from that. So I think these are all really, really interesting things you could potentially do in this kind of framework. And I think, yeah, I think that's it. So here's some references. I can also send the slides to Juan, and if he wants to hand them around. And with that, yeah, I'm happy to chat. Take any more questions.
Yep. Thank you very much, Aleks. Let's clap for Aleks. Yeah, thank you so much. It was a great talk. We were really excited about it, and yeah, it was pretty good. Thank you. So, are there any questions or comments for Aleks?
Sort of bring the chat up here. Sometimes I find it takes longer than you expect for someone to find the unmute button, even. So
yeah. Yeah, if no one has a question as of right now, yeah, can I ask a few questions about the construction of the star autonomous category?
Sure. Yeah.
So I guess what properties does this construction have? I mean, it's obviously, I would say, two functorial, or I don't know, whatever. But does this have like a closure properties, or is this universal in some way?
Yeah, that's a good question. I think it's not even totally obvious if this thing is a two functor.
Right.
So if it's a functor on cat.
Yeah.
And I think this question of whether the thing is functorial is actually very related to this question about necessary and sufficient conditions.
Okay.
Because you can think about taking a free category and doing this kind of cause construction to it, and then the free category will have an embedding into some sort of non-free category by universal property.
Yeah.
And then if the cause construction is functorial, then you get an embedding of cause of the free category into your causal category of stochastic maps or what have you. And this is actually quite a strong statement, particularly because I think actually having a functor is maybe not so strong, but if it's a star autonomous functor, then the fact that this preserves the duals really tells you a lot about how strong this logic is. So yeah, that's a good question, and I don't know the answer to it. So.
Okay. Yeah, I thought the functoriality would be okay. Yeah, thank you very much. Yeah, I think Akif has a question for
I mean, it might be. I'm not very familiar with star autonomous categories, but can it be relate? I mean, the construction of cause. I mean, can it, in some cases at least, can it be related to true construction, or is it similar?
Yeah, it has a similar spirit to the Chu construction. I think maybe it embeds in the Chu construction. but in this kind of sense, like kind of everything embeds in the two construction. It's this thing that which is, you know, it's very general. You get these kind of nice full embeddings. So the actual.
So how this
there's
construction?
Yeah, there's a paper by Hyland and Schalk about gluing constructions to get models of linear logic. And there they give a lot of different kinds of categorical constructions, and these all give you star autonomous categories. And the cause construction is an example of one of those gluing constructions. I think it's called something like a strict double gluing with a focus or something like that. So you can. And we actually say what exact construction it is in this paper. So this first archive paper, we give the reference to Hyland and Schalk and kind of point to the section which has the abstract construction. But I think gluing constructions and chew constructions are very similar to each other. They have this kind of similar spirit that you sort of make triples of an object and some extra structure, and then things need to preserve those triples in a certain way.
Is it like the construction at the discarding of, or?
What's that?
I mean, how? I mean, the discarding, does it play a role in the construction to make it like cause?
So the discarding doesn't play any role in it being a star autonomous category.
Oh.
So you don't need any of that discarding structure to get the star autonomous sort of coming out. Where it does play a role is I mentioned that you should have a kind of a nice discarding map. So it satisfies some properties. And this is what you can use to draw these conclusions, like that the tensor product of two things is a non-signaling process. This comes from some assumptions about how discarding behaves in your base category. But the double gluing thing works for any. In fact, it works for any star autonomous category, and a compact closed category is a degenerate kind of star autonomous category, so it works for any compact closed category.
Thanks. Thank you.
Yeah, I think Jack has a question of where the slides will be available. Yeah, if Aleks is okay with it, we can post it on our. We can post them on our website. So
yeah, that's fine. I'll probably put them on my site if I don't have a version similar enough to this already as well. But yeah, you're more than welcome to put them on your group website.
Thank you. Yeah, thank you very much for the question, Akif. I think I had a similar question with the chew construction. Well, if there are no other questions right now, so why wouldn't you use like higher categorical stuff to model higher order processes? I mean, what would that? I know. Well, so the internal logic of star autonomous categories. I mean, it all looks very nice, and you have this machinery to tell you when two things are composable or not. But I don't know. Like in principle, when you started thinking about this, how did in principle star autonomous categories were a better choice than higher categories? I guess that's my question. I'm sorry.
I see. So, where did this come from? Yeah, I mean, I guess it never really occurred to me to look at higher categories for this. I mean, it's a very rich language, so there probably is a higher category story here somewhere. Where the star autonomous categories came from was actually there's a concrete version of this this kind of type system, which was done by Paolo Perinotti. It's actually this second reference here, causal structures and classification of higher order quantum computation. So what Paolo did is he gave some types, and he did everything very concretely for quantum channels. So this was really coming up with a type system that you could impose on, they're called Choi matrices. So these big positive operators, which represent higher order channels. And I stared at the rules of his logic, and it just occurred to me that, oh, that's a star autonomous category. So in fact, I would say almost 80% of this first paper was just kind of looking at Paolo's paper and realizing that it's really a star autonomous category. That's what's going on there.
Okay. Yeah, thank you so much. Well, just I guess a final question from my side. How would you picture, how should we picture if we know, so if we have our cos C for a compact closed category that we like, I guess, and then we want to complete our logic, and then we would need this sec connected, and we know how to picture the tensor product and the par. How should we picture this, the sec connected?
That's a good question, which I don't have a clear answer to yet. So it has something to do with having a map which kind of behaves like a constant in one direction. Okay, so you can think about the par. So maybe if I think about like A star par B, I can just kind of think of this as or maybe it's just A par B. I can kind of think of this as kind of being a map from A to B, kind of a generic map from A to B or a generic map from B to A. The tensor product is kind of like I have a constant map from A to B and a constant map from B to A. And then the seq is kind of like it's a generic map from A to B and a constant map from B to A. So it sort of lives in between those two.
Okay.
But this is only a very rough intuition. I think our ideas are still a bit half-baked on it.
Mm-hmm. Okay. And so, like, well, okay, yeah, no, I think that was yeah, I'm happy with that. Well, also you mentioned the possibility of constructing, yeah, the cos C for like different C's and getting interesting stuff. So what kinds of C's? Well, you said that was like a good, I don't know, a question, but you have some interesting C's in mind that you can try this cos construction in, apart from the classic and quantum compact those categories.
Yeah, so you can look at the category of relations. So where your objects or sets and your morphisms or binary relations between those sets. And this gives you a sort of, it gives you a category of higher order non-deterministic processes rather than higher order probabilistic processes.
Sorry, Alex, I think you froze. I didn't get the last part. I'm sorry.
So yeah, if I do this to relations, I get higher order non-deterministic processes rather than higher order probabilistic processes. So this is an interesting, kind of an interesting one to look at that's got a slightly more discrete logical flavor than the probabilistic one does. some things go a bit strange in relations, partly because your scalars aren't cancelative anymore. So somehow probabilities tell you much more than possibilities, right? So getting something with probability 1 is a really strong statement, but getting something that is possible, all that's telling you is that it's not probability 0. So some things that we used in the original paper, the 2017 paper, start to break down a bit if you look at relations. But I'd really like to come up with some other examples. It'd be nice if you could look at categories with event structures or Petri nets or these kinds of things where people do talk about causality. Look at those kinds of categories and see if there's something interesting there. Are you saying you're muted? I don't know if you were saying something there, Juan, but maybe not. Okay. Right. You might have frozen. Okay. Your mic is still showing. Oh, there you're back. Yeah. Okay. I think, well, it's not showing as muted, but I can't hear you. Anyway,
there's some people talking about
I can't really hear you anymore. So, or it's very soft.
Yeah, I think yeah, my microphone.
Okay, that's a bit better now.
Oh, okay, great.
Yeah.
Yeah, I think I just had a question about thinking about the cost construction for things like or cost categories where people do talk about causal.
Mm-hmm.
But maybe that's
Okay.
yeah, I'm sorry.
Sorry, I might have missed the question part there. Yeah, it's still fairly soft. Maybe this is a natural point to finish. If a lot of you are on the category Zulip, I might lurk around there for a little while if people come up with questions a bit later on. Happy to answer them there. Okay, yeah, thanks for inviting me. This is happy. Always happy to come talk on these kinds of things. Yeah, well, it happens. It's the world we. Well, I mean, the flip side of this is, you know, I'm giving a seminar in Mexico right now, so you know, that's pretty cool. So technical issues aside, this is not too bad. Yeah. So, all right. Well, yeah. Thanks again, and yeah, I'll talk to you soon. Bye, everyone.
Thank you very much.
Now can you hear me? Yeah, Akif, can you hear me?
I can.
Okay.
But by the way, I was gonna ask about when should I send abstract? I mean, is it okay to send it a week before the talk? next.
Yeah, just send it to me maybe so the Wednesday before the talk.
Okay, yeah.
Yeah.
I mean, next week I can send the abstract
Okay. Yeah.
and the title.
How did
And-
you like the talk?
And have a nice day. So.
Yeah, you too.